Log on, tune in, find out. Another good idea from Cambridge.
11 o'clock, so I guess we kick off. At least we kick off. What's going on?
Just the paper.
So in this next session, we've got a sort of double act. The Goldstein-Rougier framework, or the Rougier-Goldstein framework. I don't know which way it is, but anyway. Jonty is going to kick off talking about a statistical emulator for HadCM3.
Thank you, Richard. Good morning, everybody. It's always intimidating to speak after Michel. So this is work that I've done while in collaboration with, particularly with Tamsin Edwards and Matt Collins. While I've been here at the Institute, I think optimistically when I started this work, I thought it would take a month or a month and a half, and it's taken about 5 months, and it's still very much ongoing. And what I want to do today is just explain what it is that we've been doing, and in particular, what exactly an statistical emulator is, why we need one, and what it can tell us. And I'm not going to go into the details of precisely how you do emulation, because I know that's going to be covered by Peter Challoner this afternoon. So this is a much more general talk about, which we could call something like learning about HadCM3. I mean, that's really what this talk is about. Okay? The wonderful HadCM3. So this is, I hope these pictures come out okay. This is an example of what I would term one run in our experiment. So our experiment is designed to look at the difference between last glacial maximum and mid-Holocene climate compared to pre-industrial climate. And this is just a snapshot of one tiny part of the output we get from our experiment. So in this particular case, what we've done is we've taken HadCM3 in its standard parameterization, and then we've integrated it twice, once with pre-industrial boundary conditions and once with mid-Holocene boundary conditions. And then we've looked at the anomaly in North American summer temperatures, MTWA, mean temperature of the warmest month. Okay, so this is a picture that you would get from one run of our simulator, where one run involves 2 integrations, and each integration is for a specified set of parameters and goes forward in time until stabilization, and then you take a 20-year average, and this picture is the difference of those 20-year averages. Okay. Now that sounds simple, but and we have 103 of these runs, and I just to celebrate the fact that we do have so many runs, and just to acknowledge the huge amount of work that goes into them, I'm actually going to show you them all. So, and this is really because if you haven't done it, to do one run of this type of experiment is a bit of an overwhelming thing. It's just huge, and at the center of this experiment is Tamsin Edwards, who's been like a spider at the center of a web, trying desperately to retain her sanity in this 3-year, incredibly intensive and difficult experiment. So we're showing all of these runs simply to acknowledge and celebrate Tamsin's enormous dedication and skill, basically. So well done, Tamsin. So here they are, and they do change as we go through. You'll see that every run is different. The color scale is the same. Most of these runs are done with an atmospheric model coupled to a slab ocean, and some are done with a dynamical ocean. I'll come back to that later. But there they all are, and you can see that that going as a whole, as you would expect, the predominance of blue over purple indicates that HadCM3 thinks that the mid-Holocene was warmer than today in North America, and that's entirely in keeping with our understanding of the effect of precession, which meant that northern mid-latitudes had warmer summers than they do today. Okay? So that is the basis of our experiment. 103 runs of HadCM3, each involving 2 integrations to calculate, in this case, a map for North American summer temperature anomalies at the grid scale, which is 3.75 degrees by 2.5 degrees. So those are the individual color blocks that you can see on that picture. So our objective then is to understand more about HadCM3 on the basis of these 103 runs. So what we did in these 103 runs is we perturbed in each run the parameters of HadCM3. And we have 32 parameters in total, 18 continuous, 11 switches, and 3 multi-level factors. And they controlled various aspects of mostly of the subgrid scale parameterization of HadCM3. So we perturbed things inside the ocean dynamics. That was just a switch. We either had a slab ocean or a dynamical ocean. Atmospheric dynamics, large-scale clouds, convection, sea ice, radiation, land surface, and boundary layer. So across those large-scale headings, we had 32 different parameters that we could move around. And those 103 runs represent 103 different combinations of perturbations to those 32 parameters. And in every case, the spin-up was to stability, so we didn't have to worry about perturbing the initial conditions particularly, although internal variability turns out to be a big problem, which I'll come back to. So if you have 103 runs, you will appreciate that they do not really fill a 32-dimensional parameter space, okay? Not even remotely. That 32-dimensional parameter space has something like 1,000 cubed corners, okay? So that's obviously that's going to be hard to fill with 103 runs. So what we would like to do for the purposes of calibrating HadCM3 and also for the purposes of reconstructing mid-Holocene temperature and so on, is we would like to be able to evaluate HadCM3 at any point in the parameter space. But clearly we can't, because to collect this ensemble together alone has taken many years. I mean, the QUAMP experiment started almost 10 years ago, and this is the Paleo-QUAMP extension, and that's been going for nearly 4 years. So we pretty much have to stick with the runs that we already have, but we would like to know what would happen if we ran HadCM3 at this particular combination of parameter values. Because then what we can do is we can compare HadCM3 output at those parameter values to measurements that we make on the climate system, and then we can rule out bad choices of parameters because they just don't look like the measurements. Okay, so that's part of a calibration exercise. And we can also do reconstruction, and that also includes prediction for projections for future emissions. So the framework for taking the 103 runs that we've got and turning them into a system for predicting what HadCM3 would say at any choice of parameter values is termed an emulator. So the first problem that we have to tackle with HadCM3 is its internal variability. And internal variability wouldn't be a problem if we could afford to run each integration, right, through stability and then for a very long time average. We could damp out internal variability by taking very long time averages because we're dealing here with steady state. We can't afford to do that. In fact, our time averages are only 20 years each, and that's not nearly enough to dampen down internal variability. So on top of each signal that we have, we also have some noise, which effectively comes from the fact that every time you perturb the parameters, you create an effective perturbation in the initial conditions. And when you perturb the initial conditions in a simulator like HadCM3, because it's very sensitive to its initial conditions, you generate the possibility of large changes as you go through the integration, exactly as Tim Palmer showed yesterday. So this is just a framework which I'm not going to go into in detail, but we have a framework for understanding how it is possible for us to extract from the HadCM3 output a smooth component that shows how the parameters affect the output, if you like, of the mean simulator, and then a noisy component which effectively packages up the role of internal variability. So we can take any run of HadCM3, which we think of as somewhat stochastic because of its sensitivity on initial conditions, and we can break it down into a mean term and then an internal variability term, and this is the term that would go to 0 were we able to make long enough time averages. Okay? And then as a further step in this statistical framework, what we can do is we can take, under a series of simplifying assumptions, a long control run from HadCM3, and such runs exist, they go out for thousands and thousands of years, and we can estimate reasonably accurately from the control run a variance structure for the internal variability. So for those of you who are aficionados of statistical modeling, what we have here effectively is a nugget in a stochastic process that decorrelates the moment you move away from the point R to another point R prime. And that's the framework that we use for capturing internal variability. Now that is not the only problem that we have. The other problem is something that Michel has already talked about this morning, and it's absolutely key in understanding how we use HadCM3 to talk about real climate. The fact is that HadCM3, for all its many wonderful properties, is a very poor representation of actual climate. Okay? Because we know that climate is so complex that even a code that's 1 million lines long, right, is not going to do a good job of capturing all the wonderful micro macro scale variation that we see in the actual climate system, especially when you couple together the atmosphere, the ocean, the cryosphere, the biosphere, the chemistry, and so on. So although it's tempting to try and model, right, all of the HadCM3 outputs directly, the fact is we don't think that all of those outputs are equally informative about reality. Okay? So we have here an opportunity for some quite substantial dimensional reduction. Right? Instead of thinking about all 337 grid cells that tile North America, right, we have the opportunity here to say, actually, if we think about all these grid cells, there are going to be some linear combinations of grid cells that we think are really quite reliable, but there are going to be other linear combinations of grid cells that we think are probably not very reliable, right, in terms of representing real climate. And the classic example of that would be that if you went down to the individual grid cell, right, that's the 3.75 degree by 2.5 degree tile, that's actually the solver grid cell. Okay, that's the resolution of the solver of HadCM3. Now, we know that you don't really capture dynamical systems at the resolution of the solver. Right? If you're a very gung-ho climate scientist, you might think that you start to capture processes that have characteristic length scales that are 2 grid cells wide. Right? But if you talk to a more cautious ocean scientist, right, they would say you don't even start to capture processes until you have about 10 grid cells of characteristic length, because that's about the resolution at which you can really start to see a well-shaped sine curve emerging. Okay? So we're not expecting to drill down into HadCM3 output to the grid cell level and actually say this is a realistic representation of actual climate. What we are expecting to do is to take larger scale averages of HadCM3 output and think of those as actually containing information about the system. So our challenge here is, having parked the problem of internal variability, to take the mean function from the simulator, we just had internal variability removed, and focus on those aspects of it that we think are informative about actual climate, and find a way to park the rest in a way that doesn't interfere with our inference. I don't know if Michael is going to touch on this subject in his talk afterwards. Are you going to go on to that, Michael? Okay, good. Right. Sounds good enough to me. So here's how we actually proceed in this case. Now, this has some similarities with the use of empirical orthogonal functions, but I'm going to say in a minute why it's fundamentally different. What we do is we imagine that we can specify, using our judgments and using our experience of HadCM3 and our knowledge of empirical regularities from the measurements, we're going to assume that we can specify linear combinations of the mean function of HadCM3 output that are reliable indicators of actual climate. And I can operationalize the notion of reliability, but I don't want to go into details here. Just suppose that we can do that. And the kind of linear combinations I'm thinking of, I will show you pictures of them in a minute, but these are large-scale features of HadCM3's North American output. So you might imagine that HadCM3 will get the average temperature anomaly over North America about right. Okay, that's very large, that's continental scale. You might also imagine that it gets the rough profile, zonal profile over latitude about right. And you might imagine that it can contrast, for example, coastal with non-coastal regions, or high with low regions, or high albedo with low albedo regions. I mean, those are the kind of things that we're talking about, and I'll show you the pictures in a minute. But that's really what's going into this matrix here, D. D is a collection of linear combinations that we think HadCM3 can reliably construct, reliably in the sense that they are genuinely informative about the underlying climate system. And the idea here is that if Q is the number of outputs in our HadCM3 run, that's 337, then K is a much smaller number of linear combinations that actually carry information. And this is just a little piece of mathematics here. What we do is we project the mean function from HadCM3 onto the column space of D. Okay? And this is a projection operator here. It's actually D plus, where D plus is the Moore Penrose inverse, and then it's the transpose. Okay? That's just a little piece of mathematical magic. It's how you project onto column spaces. Okay? And the interesting thing about this expression here is we're saying that actual climate, for good choices of the parameters, actual climate is the mean function of HadCM3 projected onto the column space of this set of linear combinations. But if you actually unpick this expression here, so you take the transpose inside, then you end up working with D plus trans, that's the transformation of D trans M, and d trans m is a reduced dimensional representation of HadCM3. So m is HadCM3's mean function. That's HadCM3 with internal variability removed. D trans m, right, is a small collection of linear combinations of HadCM3's mean function, right? And whereas m is q-dimensional, where q is 337, right, d trans m is k-dimensional, where in our case k is 12. Okay? So the key thing here is when we're thinking about HadCM3, we don't think about it as a 337 dimensional point, okay, 337 dimensional vector of outputs. We think of it as a 12-dimensional vector of outputs, which then gets boosted back up to 337 dimensions by this process of projecting through the column space. Okay? So the key thing is we're working in this dimensionally reduced space here. We're not emulating the whole of HadCM3's mean function. We're emulating linear combinations of HadCM3's mean function that we judge to be reliable indicators of actual climate. Okay? And that just goes on to say actually how we're going to estimate this mean function. I'm not going to go into this today. This is probably the least secure or robust aspect of what we're doing right now. I have pictures, but they may be subject to change in due course. But what we do effectively is we find a way to span this function here, d trans m, with a collection of specified functions of r with uncertain coefficients. So this m of r becomes a statistical object which itself is uncertain and about which we learn through the ensemble. Okay? I'm going to brush all that under the carpet and let Peter take care of that this afternoon. Okay? All right. So now we come on to the nitty-gritty of actually what happens in practice. So that is just a framework. It's a two-stage framework for thinking about climate simulator output. We have to have a framework for separating the signal from the noise, that is, for stripping out internal variability. And we need a second framework for allowing us to focus on the reduced dimensional expression of HadCM3, which we think is actually informative for actual climate. Okay? Now that doesn't rule out us being able to reconstruct climate at the grid cell level. It's just that when we reconstruct climate at the grid cell level, it won't have 337 dimensions, it will only have 12 dimensions. So this is a picture of our choice of filtering matrix. The colors are a bit washed out, but broadly speaking, I'm going to assert, and this is me, but Matt and Townsend did not howl, nor did Michel for that matter. So I guess that these choices are probably okay to first order. I'm going to assert that the reliable features of HadCM3 output are, first of all, the continental average. So this is entirely blue splodge here indicates that we've taken a linear combination which is the same number times every single grid cell. Okay, so that's just a mean. And then three basis vectors to capture the latitudinal or zonal gradient. So this is cos latitude here, going from positive values to negative values. This is cos latitude squared, so positive, flat, negative, flat, positive. And this is cos latitude cubed, which obviously has more bubbles in it. So we're thinking that HadCM3 should be reliable in producing roughly a cubic representation of the zonal temperature anomaly in the mid-Holocene. And then I've also included orography. Each one of these pictures is somewhat orthogonal to the picture before it because there's a whole layer of orthogonality going on here, or orthogonalization by Graham-Schmidt actually. So each additional picture is the new contribution having orthogonalized with respect to the previous contribution. So this one is the first one. When you orthogonalize latitude with respect to mean, nothing happens. But this one here, for example, carries with it some of the signal that comes from the previous latitude pictures. We tried a few other things, but they didn't seem to make any difference at all. I reckon that probably it would be insulting to the modelers to say that 6 degrees of freedom was enough for the whole of North America. So I went for a few more. Also because I wanted to capture an interesting lobe. I mean, if we went back to the original pictures, there's a sort of lobe of signal that comes in here, which looked like it was systematic, and I wanted to capture it. And so what I did is I then padded out my choice of 5 basis functions here with some principal Kriging functions. This is a very beautiful technique that allows you to construct spatial basis vectors with particular correlation characteristics that are in some sense well chosen with respect to a previous set of basis functions that you've already specified. So these principal Kriging functions are a way of padding these choices that we've already made here. So this one looks like a tricolor, for example. It's because the first low order pattern that it can't find in the basis functions we've already specified is a longitudinal pattern. So that's what you see here. Now we drilled all the way down to 12 basis functions in total, but actually there's quite a lot of evidence to suggest that we needn't have gone this far. Okay, so there may not be 12 dimensions of signal in HadCM3 output with respect to parameter perturbations, but 8 seems about right. Now we can immediately ask whether that's done a good job of dimensionally reducing HadCM3, and we can just verify this visually. So these are just pairs of plots. So this is a pair, and this is a pair, and this is a pair. I've just selected 8 runs at random, and on the left-hand side of each pair I've shown you the raw HadCM3 output. On the right-hand side I've shown you the projected HadCM3 output, where it's been projected through the column space of this D matrix that I've just shown you. Okay? And as you eyeball those, they don't look too different from each other. They're obviously smoother, because the projection is a smoothing operator. But by and large, the large-scale features of HadCM3 have been preserved through this reduction from 337 dimensions to 12 dimensions. Now you might ask, is this the same as using empirical orthogonal functions? The answer is definitely not. Empirical orthogonal functions, that is effectively the left eigenvectors from a long control run of HadCM3, are an operationally defined property of HadCM3, right? What I've done here is I've taken an extra step, and I've created basis functions that are genuinely a description of our judgments about the relationship between HadCM3 and actual climate. So those are two totally different things, right? One is a property entirely of the simulator, another is a property of our judgments about the relationship between the simulator and actual climate. So you may choose to say, I'm going to say that the EOFs of the HadCM3 control run actually also summarize my judgments about HadCM3 and actual climate, but you don't need to, right? You can have separate judgments about that, and that's what we've done here. We haven't used EOFs, we've made judgments that are broadly about the large-scale features of HadCM3 output that we think are actually reliable indicators of actual climate. So, the first question, of course, is how well does one's emulator work? And this, of course, is the key question, because emulators are very complicated statistical objects. And I just have some diagnostics here. I call them stegosaurus plots because they look like stegosauri. And I have a nephew who is very into dinosaurs. So they do look a bit like stegosauri, don't they? So this is just a random collection of 24, maybe, of the 103 runs that we have. And in each one here, I've taken the actual value of the run and shown that in red dots, and then I've predicted what would happen in that run using every run in the ensemble but the run that I'm looking at. Okay, so it's a leave one out diagnostic, and what we want to make sure is that the dots lie on the bars. Okay, and although I can do this in full North American space, I've actually just shown the zonal averages here, because then we can actually see the dots and the bars in the same picture. And by and large, these look absolutely fine. There are well-known problems with the slab ocean, and this one here is an example, and I think this one here probably is as well, which is a sort of a problem in the tropical region. We obviously want to go back and have another look at those runs. They're behaving a bit strangely, but by and large, this is a very reassuring diagnostic. And if I showed you all 103, you'd be satisfied that the emulator that I built, that I'm not really talking about, is doing a good job of allowing us to predict exactly what HadCM3 would do at parameters which we haven't actually incorporated into the calibration set. Okay, so every one of these is a leave one out diagnostic. So that's reassuring. Now, I'm close to wrapping up actually. So what happens next? Well, we're going to use the emulator very briefly to tell us things about our experiment, and in particular about HadCM3. We can, for example, work out what are the main parameters for influencing HadCM3 output when we're talking in particular about North American MTWA mid-Holocene anomalies. And these are our basis functions here. This is the flat mean, these are the 3 latitude terms, this is the orography, and these are the padding functions in space. And here are some of the parameters that turn out to be important. And there's a range of parameters here. This one, for example, is the sea ice. This one is the radiation scheme. That's clouds. That's clouds, that's entrainment, that's convection. Here's one from the land surface scheme. But the thing that stands out here, if you're looking at the size of these coefficients, is this clump of large numbers here, okay? Which is the sulfur cycle, which is a switch, which is either on or off, and the vertical gradient of cloud water, which is an aspect of the large-scale cloud scheme, which is also a switch, which is either on or off, and coupled, which switches in and out the dynamic or the slab ocean. Okay, and this is the thing that we want to investigate because this is where all the signal is. Okay, so why is it that fiddling with these parameters makes such a big difference to North American mid-Holocene temperature anomalies? This is the kind of diagnostic that we can generate with an emulator that we couldn't generate with a simulator because the simulator is too expensive to run. In each of these pictures I focused on one particular parameter, and the solid line is the same in every case. This is the zonal response at the standard parameterization, and then for each panel I've taken one of the parameters and I've moved it to either a medium value or a low value away from its standard value. So in this one here, for example, the thick line is black, so the standard parameterization is low, and the red line is a medium setting and the blue line is a high setting, and you can see the effect of this cloud scheme parameter is to change the zonal profile of the temperature anomaly. The acceptor of this parameter, for example, is to accentuate the mid-latitude, right, positive anomaly. So we have a very direct interpretation here about what it means to change a parameter in HadCM3. This would be a very expensive picture to compute because you'd have to run HadCM3 once for the standard setting and then twice more for each of these. And that was a feature of the early QUAMP experiment actually, but we could do this for any of the parameters and for any combination of parameters. Yeah? So to show you the combination of parameters, this is what's going on in that coupling of the vertical gradient of the cloud scheme and the sulfur cycle, and this is obviously pretty alarming actually. The reason this is alarming is because when you switch the sulfur cycle off, right, we're finding out that HadCM3 has cooling in the mid-Holocene. Right? Now that can't be right. Okay? So, and it can't really be the sulfur cycle either, because we just don't think the sulfur cycle is that important. So what is going on in this experiment? Well, we're only digging into this now, so I'm not going to tell you the whole story, but let me just say that what's going on here is something to do with a combination of the behavior of HadCM3, the very, very complex tasks that's involved in getting one run out of HadCM3, in particular the many hundreds of files, configuration files that have to be loaded. When the sulfur cycle is switched off, a configuration file is loaded to impose an optical depth, which is one of the things the sulfur cycle is fiddling with, and that's actually a pre-industrial configuration file which is being used here for the mid-Holocene. And also, when you run with the sulfur cycle on, very often the model is extremely unstable because the solver is not necessarily configured to handle the sulfur cycle, especially in the older versions of HadCM3 when the sulfur cycle was a new thing. And so there may be a missing not at random problem here, which is in our ensemble of 103 evaluations of HadCM3, it's quite possible that we'd have an underrepresentation of sulfur cycle on because those runs never completed. Yeah? Okay, so I'm just pointing out here that there's a ton of information embedded in an emulator which you can extract, but it's telling you not just about HadCM3, but also it's telling you about the experiment in a much larger sense. It's telling you about the code itself, the configuration files that you ran, the possibility of mistakes during the construction of the code. I did an experiment which Serge was also part of, where the entire first batch of runs, 30 runs on a supercomputer, had to be junked because when we built the emulator, it was quite clear that they'd made a mistake in their code. So the purpose of the emulator in that case was to point out the code wasn't working like they thought it was. And once again, this contrast between sulfur cycle on and sulfur cycle off is telling us something very interesting about our experiment, but it's not necessarily telling us just about HadCM3, also about the configuration, the boundary conditions, the experiment, and so on. So we do actually get error bars on these too, because an emulator is a statistical object that creates prediction with uncertainties. But you can just see here, when I put the error bars on, they're far smaller than the signal, which is so interesting. This is the same picture just to show that we can do it not just zonally average, but tiled over the whole of North America. And so these are the sulfur cycle off, which are cooler. You can see that the structure is not strictly just zonal, but also has other features too. And this is with the sulfur cycle on. And here, with the vertical gradient cloud water scheme on, you can see a much stronger intensification of the mid-latitude warming here. VGCW, another very, very twitchy parameter in HadCM3. Okay, not one you want to mess with at all unless you absolutely have to. But this is something you only discover when you do the experiment. Okay, so I guess it's not really surprising that there's an interaction between these two very, very complicated parameters. That's the fine print, which just explains the things that I've already said about how this is this is not just a HadCM3 result, but also an experimental result. So I'm just going to finish very briefly with a predictive analysis. I see my time is basically up. Okay, we wanted to do paleoclimate reconstruction. This is the problem that we face with paleoclimate reconstruction: signal to noise. Okay, at the grid cell level, which is where the paleo measurements are, right? The signal to noise is very poor. Yep. In fact, this is a decibel scale. So 20 corresponds to an amplitude difference of about 10, and 10 corresponds to an amplitude difference of about 3. And you can see that all of these northern measurements basically are swamped with noise. Okay? Every cross shows where we have a reconstruction from the Biome 6000 database. So all noise. But down here, there's hope. Okay? But in fact, obviously, although our reconstructions are pointwise on the grid cells, we're going to create linear combinations of reconstructions because that's where the signal is, averaging over larger spaces. And we can do just a little trial experiment. Here is HadCM3, where we've used our emulator to integrate out of the simulator uncertainty about the parameters. So we attached a distribution to each of the parameters, and then we've integrated that distribution out. So we've created if you like, an unconditional expression of climate, where not for any specific parameter value, but it's averaged over all parameter values. In fact, this is for the dynamical ocean and VGCW off and the sulfur cycle on and entrainment constrained, because as Tim showed yesterday, the low values of entrainment are very unrealistic. And then what we can do is we can ask how much would uncertainty fall if we were able to do reconstructions of varying qualities. And this is just 3 pictures to show how we could use our simulator and our emulator to make inferences about reconstruction accuracy. And if we can reconstruct to each grid cell at a standard deviation of 4 degrees, we get a reduction to about 0.6 of a degree in the anomaly. 2 degrees, a reduction down to more like 0.4. And if we can go to 1 degree, which is a very accurate reconstruction, we can get a reduction down to about 0.2. Okay? So we can use this framework to make predictive statements about the quality of our reconstructions. And I'm going to leave you with a summary slide there, but I'll finish. So thank you for your attention.
Dante, could you put your 12 eigenmaps up, please?
They're not eigenmaps.
I know. I couldn't think of the right word.
They're linear combinations.
Linear combinations. Not a question so much as an observation. The first one is, even though you've very carefully constructed your regressor functions, the residuals will be correlated, and the residuals from each of these 12 will be correlated with one another. Possibly.
No, I don't understand your point.
When you're emulating the first one, for example, there will be a residual, and that residual may well be correlated with the residual of the second one.
So we emulate them jointly, not independently, individually.
I understand that, but the next point is that the roughness lengths may well be different for the different maps.
Okay, so what's going on here?
I can deal with this with my techniques, this is why I'm mentioning.
Yeah, so what's going on here really is that in some ways internal variability, although it's the bane of our existence because it's so noisy, actually is also really helpful because it masks low-order effects which you think might or might not be an issue. So basically what we do in this framework is we pull out the large-scale signal and we just assume that everything else has been swamped by the internal variability at the grid cell level, and that's really what's going on here. Okay, so internal variability is a pain, but like any independent, identically distributed random quantity, it actually simplifies the modeling quite a lot.
Chris?
To what extent did you use the emulator and the results from previous runs to decide where best to next run the simulator?
That's a very good question, because that's exactly how you should do it in practice.
That's why I asked.
In the original quant experiment, we did that quite a lot. I can defer to David here. Where is David? Yep. But after the initial parameter perturbations, we spent quite a long time, didn't we, trying to work out where to do the next set of runs. And that was based on very crude emulation type frameworks. The key thing that you have to bear in mind, though, with these kinds of experiments is they generate a resource which is available for the entire community. And although you may be driven by one particular research question, like climate sensitivity in our original case, or mid-Holocene temperature anomaly in this case, the fact is that you don't want to tune your ensemble to one particular research question if it's going to be used for many different research questions. So you always have to balance in this situation that the choice that you might want to make for your next run of the simulator, based upon what's most informative for your experiment, based upon the emulator that you have built so far, and also the more general run that might be useful for other people who aren't necessarily interested in the mid-Holocene, but in precipitation, for example. Or
so there's a very good question there, is what would be the best set of runs to do to optimise the value to other people?
Yeah.
So it's still an experiment.
And that's actually something that's been touched on in this Newton Institute program. And I know Chris Farrow and Dave Stevenson and a few other people have been thinking about this.
Anything there? Yeah.
Just a very general question. I mean, you based this on HadCM3, and I mean, there is an argument that's about the worst choice of model you could have made to try and emulate, because it's neither a state-of-the-art GCM on the one hand, and neither is it a simple model to understand.
Yep.
So my question really was, have you, I mean, there are classes of models which say run at T21, I mean, really low resolution, but still have continental structures and nonlinear dynamics and chaos and so on. I mean, can one sort of demonstrate the utility of these methods on rather more simple GCMs that you really can do many thousands of runs without, you know, busting the computer? And then really try to develop it on the sort of state-of-the-art model.
So I think our dream is rather more grandiose, actually. Right? We would like, right, the current commissioning of HadCM3 to be statistically well informed. And in particular, we would like the calibration exercise which is currently going on, the tuning of HadCM3's parameters, to be as rigorous as possible. And therefore, we need to demonstrate in the next best thing to HadCM3, which is currently HadCM3, right, how constructing an emulator of HadCM3 is actually possible and how it adds value in the process of understanding how HadCM3 actually works. So HadCM3 for us is the test bed that we hope will convince people that instead of doing one-at-a-time ad hoc tuning procedures for HadCM3 and similar types of code, they should actually think about doing a principled design, running an ensemble of parameter perturbations, and then hiring a statistician to construct an emulator that will help them to understand HadCM3 better. Okay, so we're thinking in that direction, I think, more than anything else.
Down here and then Dave.
Are you just
follow on point really to
okay.
that, because in practice what happens is that, for instance, a lot of the parameters will come from the numerical weather prediction. So people who actually do the weather forecasting will have a set of parameters that they prefer, and at HadCM3 a lot of the parameter values that they use are inherited from that weather forecasting. So also HadCM3 is it takes a very long time to run. So in practice what will happen is we'll only be able to do these kind of ensembles where you play around with model input parameters much later than the standard HadCM3 run is arrived at. So it sounds nice, but in practice it doesn't work like that.
okay? One final question before.
There are three variables here. One is the input, that is your perturbation to your parameters. Then you have a state, and then you have an output, y. Y is your observation that you would like to compare. Now, if I look at proper ordinal decomposition, this is between the input and the state. Now, you want to now look at the y as the quantity to figure out what are the modes that you would like to take. If I change my y, I will get different modes.
Mm-hmm.
So this is going to be completely based on what kind of observations I've done. Right?
Yeah, absolutely. Yeah, we all know that a careful choice of calibration data can make your model look great or rubbish. Yeah? That's just part of the judgment, isn't it? It comes back to what you take out of your model that you think is reliable, and what you leave to one side because you think it's unreliable.
This is what we call balancing between the input and output. Instead of looking at the input in the state as in TOD, what we are looking at is the input perturbation and the output y. And this particular scheme that you are doing is called balancing in engineering.
Right, balancing.
Balancing.
Okay, thank you.
Okay, I think we will wrap that discussion up there because it gives us 30 seconds for a speaker swap. So thank you again, John T.